A first application, the bipartite matching problem. Having developed a set of powerful algorithms for the maximum flow problem, we now turn to the task of developing applications of maximum flows and minimum cuts in graphs. We begin with two very basic applications. First, in this section, we discuss the bipartite matching problem mentioned at the beginning of this chapter. In the next section, we discuss the more general disjoint paths problem. The problem. One of our original goals in developing the maximum flow problem was to be able to solve the bipartite matching problem, and we now show how to do this. Recall that a bipartite graph G equals to V is an undirected graph whose node set can be partitioned as V equals to X union Y, with the property that every h little e in capital E has one end in X and the other end in Y. A matching M in G is a subset of the edges M, which is subset equals to E, such that each node appears in at most one edge in M. The bipartite matching problem is that of finding a matching in G of largest possible size. Designing the algorithm. The graph defining a matching problem is undirected, while flow networks are directed. But it is actually not difficult to use an algorithm for the maximum flow problem to find a maximum matching. Beginning with a graph G in an instance of the bipartite matching problem, we construct the flow network G' as shown in figure 7.9. First, we direct all edges in G from X to Y. We then add a node S and add an edge SX from S to each node in X. We add a node T and add an edge YT from each node in Y to T. Finally, we give each edge in G' a capacity of 1. We now compute a maximum ST flow in this network G'. We will discover that the value of this maximum is equal to the size of the maximum matching in G. Moreover, our analysis will show how one can use the flow itself to recover the matching. Analyzing the algorithm. The analysis is based on showing that integer-valued flows in G' encode matchings in G in a fairly transparent fashion. First, suppose there is a matching in G consisting of k edges xi1, yi1, xi2, yi2, xi3, yi3, and so on until xik, yik. Then consider the flow f that sends one unit along each path of the form s, xij, yij, t, that is f of e equals to 1 for each edge on one of these paths. One can verify easily that the capacity and the conservation conditions are indeed met, and that f is an ST flow of value k. Conversely, suppose there is a flow f' in G' of value k. By the integrality theorem for maximum flows 7.14, we know there is an integer value flow f of value k, and since all capacities are 1, this means that f of e is equal to either 0 or 1 for each edge e. Now consider the set M' of edges of the form xy on which the flow value is 1. Here are 3 simple facts about the set M'. 7.34. M' contains k edges. Proof. To prove this, consider the cut a, b in G' with a equals to the set of S singleton union X. The value of the flow is the total flow leaving A minus the total flow entering A. The first of these terms is simply the cardinality of M', since these are the edges leaving A that carry flow, and each carries us exactly 1 unit of flow. The second of these terms is 0, since there are no edges entering A. Thus, M' contains k edges. 7.35. Each node in X is the tail of at most one edge in M'. Proof. To prove this, suppose little x in capital X were the tail of at least 2 edges in M'. Since our flow is integer valued, this means that at least 2 units of flow leave from X. By conservation of flow, at least 2 units of flow would have to come into X. But this is not possible since only a single edge of capacity 1 enters X. Thus, X is the tail of at most one edge in M prime. By the same reasoning, we can show that 7.36. Each node in Y is the head of at most one edge in M prime. Combining these facts, we see that if we view M prime as a set of edges in the original bipartite graph G, we get a matching of size K. In a summary, we have proved the following fact. 7.37. The size of the maximum matching in G is equal to the value of the maximum flow in G prime, and the edges in such a matching in G are the edges that carry flow from X to Y in G prime. Note the crucial way in which the integrality theorem 7.14 figured. In this construction, we needed to know if there is a maximum flow in G prime that takes only the values 0 and 1. Bounding the running time. Now let's consider how quickly we can compute a maximum matching in G. Let n equals to the size of x equals to the size of y, and let m be the number of edges of G. We tacitly assume that there is at least one edge incident to each node in the original problem, and hence m is greater than or equals to n over 2. The time to compute a maximum matching is dominated by the time to compute an integer value the maximum flow in G prime, since converting this to a matching in G is simple. For this flow problem, we have that C equals to the summations of CE summing for all E out of S, which is equals to the size of X, which is equals to n, as S has an edge of capacity 1 to each node of X. Thus, by using the big O of M times C bound in 7.5, we get the following. 7.38. The Ford-Fulkerson algorithm can be used to find a maximum matching in a bipartite graph in a big O of M times n time. It's interesting that if we were to use the better bounds of big O of M squared times log base 2 of C or big O of n cubic that we developed in the previous sections, we'd get the inferior running times of big O of M squared times log n or big O of M to the 3 n cubic. For this problem, there is nothing contradictory in this. These bounds were designed to be good for all instances even when C is very large relative to M and N, but C equals to N for the bipartite matching problem, and so the cost of this extra sophistication is not needed. It is worthwhile to consider what the augmenting paths mean in the network G prime. Consider the matching M consisting of edges x2, y2, x3, y3, and x5, y5 in the bipartite graph in figure 7.1. See also figure 7.10. Let F be the corresponding flow in G prime. This matching is not maxima, so F is not a maxima ST flow, and hence there is an augmenting path in the residual graph GF prime. One such augmenting path is marked in figure 7.10b. Note that the edges x2, y2 and x3, y3 are used backward, and all other edges are used forward. All augmenting paths must alternate between edges used backward and forward, as all edges of the graph G prime go from x to y. Augmenting paths and are therefore also called alternating paths in the context of finding a maximum matching. The effect of this augmentation is to take the edges used backward out of the matching and replace them with the edges going forward. Because the augmenting path goes from S to T, there is one more forward edge than backward edge. Thus, the size of the matching increases by 1. Extensions. The structure of a bipartite graphs with no perfect matching. Algorithmically, we've seen how to find perfect matchings. We use the algorithm above to find a maximum matching, and then check to see if this matching is perfect. But let's ask a slightly less algorithmic question. Not all bipartite graphs have perfect matchings. What does a bipartite graph without a perfect matching look like? Is there an easy way to see that a bipartite graph does not have a perfect matching, or at least an easy way to convince someone the graph has no perfect matching after we run the algorithm. More concretely, it would be nice if the algorithm, upon concluding that there is no perfect matching, could produce a short certificate of this fact. The certificate could allow someone to be quickly convinced that there is no perfect matching without having to look over a trace of the entire execution of the algorithm. One way to understand the idea of such a certificate is as follows. We can decide if the graph G has a perfect matching by checking if the maximum flow in a related graph G prime has value at least n. By the max flow main cut theorem, there will be an ST cut of capacity less than n if the maximum flow value in G prime has value less than n. So in a way, a cut with a capacity less than n provides such a certificate. However, we want a certificate that has a natural meaning in terms of the original graph G. What might such a certificate look like? For example, if there are nodes x1, x2 in X that have only one incident edge each, and the other end of each edge is the same node y, then clearly the graph has no perfect matching. Both x1 and x2 would need to get matched to the same node y. More generally, consider a subset of nodes A, which is subset equals to x, and let tau of A, which is subset equals to y, denote the set of all nodes that are adjacent to nodes in A. If the graph has a perfect matching, then each node in A has to be matched to a different node in tau of A, so tau of A has to be at least as large as A. This gives us the following fact. 7.39. If a bipartite graph G equals to VE with two sides x and y has a perfect matching, then for all A which is subset equals to x, we must have the size of tau of A is greater than equals to the size of A. This statement suggests a type of certificate demonstrating that a graph does not have a perfect matching. A set A which is subset equals to x such that the size of tau of A is less than equals to the size of A. But is the converse of 7.39 also true? Is it the case that whenever there's no perfect matching, there is a set A like this that proves it? The answer turns out to be yes, provided we add the obvious condition that the size of x is equal to the size of y, without which there could certainly not be a perfect matching. This statement is known in the literature as Hall's theorem, though versions of it were discovered independently by a number of different people, perhaps first by Koenig in the early 1900s. The proof of the statement also provides a way to find such a subset A in polynomial time. 7.40. Assume that the bipartite graph G equals to VE has two sides x and y, such that the size of x is equal to the size of y. Then the graph G either has a perfect matching, or there is a subset A which is subset equals to x, such that the size of tau of A is less than the size of A. A perfect matching or an appropriate subset A can be found in big O of m and time. Proof: we will use the same graph G prime as in 7.37. Assume that the size of x is equal to the size of y, which is equal to n. By 7.37, the graph G has a maximum matching if and only if the value of the maximum flow in G prime is n. We need to show that if the value of the maximum flow is less than n, then there is a subset A such that the tau of A whose size is less than the size of A, as claimed in the statement. By the max flow mean cut theorem, that is 7.12, if the maximum flow value is less than n, then there is a cut A prime B prime with a capacity less than n in G prime. Now the set A prime contains S and may contain nodes from both x and y as shown in figure 7.11. We claim that the set A which is equals to x intersect A prime has the claimed property. This will prove both parts of the statement, as we've seen in 7.11, that a minima cut A prime B prime can also be found by running the Ford-Fulkerson algorithm. First, we claim that one can modify the minima cut A prime B prime so as to ensure that the tau of A, which is subset equals to A prime, where A is equals to X intersect A prime as before. To do this, consider a node Y which is in tau of A that belongs to B prime. As shown in figure 7.11a, we claim that by moving Y from B prime to A prime, we do not increase the capacity of the cut. For what happens when we move Y from B prime to A? The edge YT now crosses the cut, increasing the capacity by 1. But previously there was at least one edge XY with X in A, since Y is in tau of A. All edges from A to and Y used to cross the cut and don't anymore. Thus, overall, the capacity of the cut cannot increase. Note that we don't have to be concerned about nodes little x and capital X that are not in A. The two ends of the edge XY will be on different sides of the cut, but this side does not add to the capacity of the cut, as it goes from B prime to A prime. Next, consider the capacity of this minima cut A prime B prime. That has a tau of A which is subset equals to A prime, as shown in figure 7.11b. Since all neighbors of A belong to A prime, we see that the only edges out of A prime are either edges that leave the source S or that enter the sink T. Thus, the capacity of the cut is exactly, that is, C of A prime B prime, the capacity of the cut, is equals to X intersect B prime, the size of it, plus the size of Y intersect A prime. Now notice that the size of X intersect B prime is equals to N minus the size of A, and the size of Y intersect A prime is greater than equals to the size of tau of A. Now the assumption that C of A prime B prime, the capacity of the cut of A prime and B prime is less than N implies what? Implies that N minus the size of A plus the size of tau of A is less than or equals to, if we replace that N minus the size of A with the size of X union B prime, and if we replace the size of tau of A with the size of Y intersect A prime, then the previous form will be less than equals to the size of X intersect B prime plus the size of Y intersect A prime, which is exactly C of A prime B prime, which is less than N. So comparing the first and the last terms, we get the claim inequality that the size of A is greater than the size of a tau of A, because N minus the size of A plus the size of tau of A is less than N, so we cancel out the N and we move the term the size of A to the right hand side. Then we get that the size of A is greater than the size of tau of A.